Okay, so we're going to get started with this first problem here. It says a pendulum reaches a maximum height h relative to the lowest height while it swings. We can ignore air resistance and friction. So here's our pendulum down here. We see that this is the maximum height that it's going to reach, and that it's going to swing from one side to the other. And this over here is going to be the lowest height. It's asking us where is the pendulum when it has maximum kinetic energy. So for this problem, we need to think about kinetic energy. And we know that kinetic energy is equal to 1/2 mv squared. We also know that gravitational potential energy is equal to mass times gravity times height. So if we're looking at this pendulum over here, we know that it has a maximum height, let's say at point A, and a minimum height at, let's say, point B. So what does that mean? Well, since at point A, the pendulum has a maximum height, that's where we're going to have a maximum GPE. And again, that's because we have maximum height here, so max GPE. But at point B, we have a minimum height, so we're going to have a minimum GPE. Some of you might be asking, why am I bringing up GPE when I was talking about KE? Well, very simple. Conservation of energy. We know that energy cannot be created nor destroyed. This tells us that energy can only go from one form to another. So what does that mean? That means that at point A, when I have maximum GPE, all of that energy is getting transferred into something else as it moves to point B. Since I have minimum GPE at point B, and since my pendulum is moving at this point, that means at point B, I'm going to have maximum KE. And then at point A is where I'm going to have a minimum KE. So again, think of it like this, right? Let's say this is point A, and let's say this is point B. As this pendulum moves, it's going to have only GPE because it's at its maximum height. So at the maximum height, we're going to say it has only GPE. And then as it moves over to point B, it's going to have no GPE because it's at a minimum height. So where did that energy go? Well, if this pendulum is moving, which we know it is, that means at point B, it's all going to go into kinetic energy. And in the beginning, at point A, since it was at its maximum height and it wasn't moving, there was no kinetic energy. So if we were to have kind of an intermediate point here, let's say like point C, we would see that at point C, we would have some GPE and some KE, meaning that some of that energy from GPE is being transferred into KE. And we see that as our pendulum continues to move, that more and more of this GPE is getting transferred into KE as we go from A to C to B. But what if we went back? What if instead of us going from A to C to B, we went from B to D to E, and then let's say this is our last point, E? Well, then we would just do the opposite, right? Our kinetic energy would now start moving into gravitational, and then more kinetic into gravitational, and more kinetic into gravitational, until our pendulum stops moving. And we actually see this happen, that if we took a pendulum, let it swing right to left, that we would notice that the pendulum is moving slowly, quickly, and then it slows down as it reaches its maximum height. And that's because its GPE is going into kinetic, and then more is going into kinetic, and then it's going in reverse. It's going from kinetic back to GPE, more GPE, and then all GPE. How do we understand how a pendulum is going to work? Let's go ahead and look at all these problems. Okay, problem 1 says, where is the pendulum when it has its maximum kinetic energy? Well, we just talked about this. Maximum kinetic energy is going to be at its lowest point, so that's going to be right here at the minimum height. Perfect. And again, that's because at this point it has all GPE, and at this point it has no GPE, which means all of that GPE was transferred into kinetic energy for a maximum KE. Let's look at the next problem. A pendulum reaches a maximum height h, same thing as before. Where is the pendulum when it has its minimum kinetic energy? Well, like we said before, at this point, right, if we call it point A, it has maximum GPE, which means that since there's a maximum GPE, there's going to be a minimum KE. In other words, where is the pendulum when it is not moving? And it's not moving at its highest point. So that's going to be right here. Pendulum reaches maximum height, just like before. Where is the pendulum when it has minimum potential energy? So remember, potential energy depends on height. So where does it have the minimum height? Well, that's very easy to see at the minimum height. Piece of cake. Same question. Where is the pendulum when it has maximum potential energy? Well, that's just asking where it has the maximum height. And if we look really quickly, we can see the maximum height is going to occur at the maximum height. All right, now we're going to start looking into some things that seem more difficult, but they actually aren't. This one says block A and block B are dropped from the same height, except block B starts from rest and slides down a frictionless incline of the same height. And the blocks are identical, meaning that they have the same mass. Something really important to understand here is that this is frictionless, okay? Which block hits the ground with the greatest speed? Well, let's think about this in terms of energy. We know that gravitational potential energy, in this case, they're both starting up here, is going to transfer into kinetic energy. We know that gravitational potential energy is mass times gravity times height, and we know that kinetic energy is 1/2 mv squared. Both of these blocks are starting at the same height, both of these blocks have the same mass, and both of these blocks will have the same gravity because they're on Earth. So they're all going to start with the same gravitational potential energy, which means that all of this energy is going to be transferred into kinetic. We know, like I said before, that kinetic is 1/2 mv squared, and we're saying that these blocks both have the same mass, which therefore means that these blocks have to have the same velocity. If they're starting with the same energy, they need to end with the same energy. Even if they had different masses, they would still have the same final speed. And we can see that really quick if we just set GPE equal to KE. We'll notice that GPE has a mass and KE has a mass, which really just tells us that gravity times height is equal to 1/2 v squared. They both have the same gravity, they both have the same height, they both will end with the same velocity. Now, block A falls vertically from height h, and block B is thrown downward with an initial speed, so this is important. So like we said before, they're both starting with GPE, except in this case, block B also has some kinetic energy. So what does that mean? Well, that means that block A is starting with less energy than block B. Why is that important? Because we know that total energy is conserved. So if we were to just give these two random numbers here, we could say this is 10 and this is 20. We know at the end that all of this energy is converted into kinetic energy, and that's the same for block B as well. Clearly we can see that block B is going to be moving faster because it has 20 joules of kinetic energy, where block A only has 10 joules of kinetic energy. The more kinetic energy you have, the faster you will be moving. Block B is our answer. A is thrown downward with an initial speed of v from a height, so block A has an initial speed of v. Block B is thrown horizontally with speed v from height h. So this one's also thrown, but this time it's thrown horizontally. Which block hits the ground with the greatest speed? So this is talking about speed, not velocity. And why is that important? Well, that's important because speed is really equal to the total velocity. So in other words, the absolute value of the Vx squared plus Vy squared, all square rooted. So if we look at this problem in terms of energy, we're going to note that block A, right, is starting with some GPE and also starting with some KE. And we have block B, which is doing the same thing. It's starting with some GPE and it's also starting with some KE. It doesn't matter that that initial velocity is pointed to the right. So it's just telling us that both of these blocks are starting with the same energy, which means at the end they're going to end with the same energy. They're both ending with kinetic energy. So all of this energy needs to be transferred into kinetic. Same for block A as well, which just means that they're both going to hit the ground with the same speed. Because again, if they have the same kinetic energy, let's say 100, we know that kinetic energy is 1/2 mv squared. Same thing here. Since these blocks are identical, meaning that they have the same mass, we see that mass doesn't matter here. So it's just telling us that 100 equals 1/2 v squared. We're going to find out that they have the same speed when they hit the ground. Block A starts with initial speed v and slides down a frictionless incline of height h. Block B is thrown horizontally with speed v from height h, and the blocks are identical. So like we said before, we have block A and we have block B. Block A initially has some GPE and also some kinetic energy. Block B has the same thing. It's starting at some height and it also has some kinetic energy. What does that mean? Well, both of these at the end are ending down here, which means that they're both going to end with only kinetic energy. Therefore, since both of these blocks are starting from the same height, they're both going to start with the same energy, and they're both going to end with the same energy, just like we said before. So really quickly, just showing that, let's say for block A, right, we have mass times gravity times height plus 1/2 mv squared, and we know that this is equal to our energy at the end, which is 1/2 mv final squared. Well, masses cancel out, we're just left with gh plus v squared equals vf squared. If we do the same thing for block B, we can see that we'll get a very similar equation. mgh plus 1/2 mv initial squared is equal to 1/2 mv final squared. Same thing, we cancel out our masses here, and we're left with the exact same equation. gh plus 1/2 v naught squared equals vf squared. We know that this v and this v are the same. We know that this height and this height are the same. We know that this g and this g are the same. Therefore, our final velocities will be the same, meaning that they will reach the ground with the same speed.